right there. So then it's just a matter of plugging in what it gives you. And then what do you end up with? 0. So what does that mean? So it has to be perpendicular. If it has 0 component in the direction of path, it's going to be perpendicular. Notice that the component of f in the direction of v is equal to 0. This makes sense since f is perpendicular to v. So what do you do for part B? The component of f perpendicular to v. So how do you find that? It's this subtraction, right? If you have f parallel and you have f, you just subtract f parallel. But what is f parallel? 0. So in this case, f perp is f. It's all the direction is perpendicular. So then you need to remember that work is equal to what? Force times. I mean, the simple way you usually hear it in physics is work is force times what? Distance. So in this case, our force vector and displacement vector, not work. You have a force vector and a displacement vector. So you do the dot product of the two things. You do the dot product of the two things. And in this case, it's going to be 0. Why is it going to come out to be 0? So if it's perpendicular to the path, why does that mean the work is going to be 0? Just logically, can you explain why?
There's no displacement in that direction.
There's no displacement in that direction. Basically, it means in a real life situation, if the only thing you can do is pick a rock up, are you able to move it side to side? Yeah, if you're only able to move a rock up and down, can you move it side to side? No, you need to be a little bit off, right? It can't be perpendicular. It can't be perpendicular. Okay, how do you feel about this homework in 3 dimensions? We have a vector w in 3 dimensions, and we have a vector, let's say, v in 3 dimensions. What could you form given these two vectors? You could form a what? Parallelogram, okay? Now, theoretically, if you can find pretty easily the area of a parallelogram in 2 dimensions, can you do the same thing in 3 dimensions? Sure. This is what the cross product is. The cross product is a vector, everybody. The cross product is a vector. The cross product is a vector that is going to be what to these two vectors? Yes. The cross product C, so W, so in this case V cross W is the vector C. And what's the relationship? The vector C is perpendicular to what? V and what? C is perpendicular to what? W. But it's not just any vector that's perpendicular to the plane. How many vectors are perpendicular to that plane? Infinite number. Here's the key. Here's the key. The magnitude of C, the length of C is equal to the area of the parallelogram. So you see this parallelogram right here? Whatever that area is, 17 square meters, how long, what will be the magnitude of C? 17. The cross product vector is the vector that is perpendicular to both W and V and is equal to, in magnitude, to the area of the parallelogram. That's what the cross product is. I'm going to show you how to find it. Yes, Stephen, and then what?
They set this magnitude of C to equal to that area. Does it help them with?
Sorry, I think I understand your question. What'd you say? And what's the next one? Oh, W1, W2, and W3. So we haven't done anything other than the setup. You with me so far? The first thing you do is you circle I, and you eliminate the row and the column that I is in, leaving you with just these. You see what I'm left with? And what do you think that you do with those 4? You do the 2 by 2 determinant. W2 times what? Minus what? W2, and that's times the I component. Remember, because I told you cross product is a what? Vector. So what do you think you do next? If you did that to I, what do you think you do next? You do the same thing, but with J. Cross them out, and what do you you do V1, W3 minus what? W1, and what's that? J. And then what do you get? K cross, and you end up with V1. You see how I'm keeping it in alphabetical order? Please do that if you can. Times what? Okay. So I'm going to show you something, and then you're gonna help me with a problem. Okay. I showed you this blue thing before. You see this blue thing?
Yeah.
Take a look at this blue thing. I'm going to copy and put it right next to what we just came up with over here. You're going to tell me if you see an issue.
You flip the J.
Oh, there's something weird going on here. What's weird? Does it match? Does this right here, does that match this? Does it match? Does this one match here? But what's wrong with the one in the middle? Oh, that was the poor choice right there. Yeah, you can't even see it anymore. What do you end up? What's in the middle here? It's almost the same, right? Oh, so here's the thing. It goes plus, minus, and then plus. So what they did, which was really annoying here, is they took that negative sign right here, and what did they do with the negative? What did they do with the negative? They distributed it in. Don't do that, okay? Remember mine. Like basically, don't remember it this way. I do not want you to remember the line. I want you to remember the method, because here's the thing. To calculate a 3 by 3 determinant, you need to calculate 3 2 by 2 determinants.
And 7 the alternate.
Exactly. You have to alternate the signs when plus minus plus minus. Here's the thing. Can you go even further? Are there 4 by 4 determinants? Yeah. How many 3 by 3 determinants do you think you need for a 4 by 4 determinant? 4 of them. And then for each of the 3 by 3 determinants, you need 3 2 by 2 determinants. So you can take the determinant of any square matrix and do it in terms of lots and lots of 2 by 2 determinants. Determinants come up all over the place. This is one of them. So what's really cool about this vector, you see this vector we just came up with right here? This vector right here is perpendicular to V and W, and the magnitude of this vector is equal to the area of the parallelogram formed by V and W. Let's just do one. Let's see what I mean. So give me 3 random numbers, Wiley. 3 random numbers.
7.
Sure.
3.
Yep. 1. And let's have Jerry, give me 3 other random numbers.
4.
Yep.
5, 6.
So theoretically, I could ask you to sketch those. Sure, it's fine. Humans are also terrible at making up random numbers. We put patterns all over the place. So totally valid though. Are those vectors? Sure. Could you make a rough sketch of them, right? They're like here, and you could draw it and be like, I could ask you, what is the area of that parallelogram, or like what is the cross product? Theoretically, with a lot of time, you have to do like 3-dimensional vectors and going up and over. With a lot of time, without what I just taught you, you could do this problem, but it would be crazy annoying. Let's do it this way. If I want the cross product of these two things, and I'm going to call this one V and this one W, how do I do that? I first have to write out that matrix. What was that matrix going to be? So V cross W. Can someone tell me what I'm going to write out here? Someone who hasn't spoken yet. What is it going to be? Soma, what is it going to be?
I, J, K.
But we are serious. Ha, not JK. Yep, keep going.
7, 3, 1.
Yep, and?
4, 5.
I know, some people like my jokes, but not all of them. Okay. So if we do this out here, what's the first product? 3 times 6 minus?
1 times 5.
And that's going to be the I component. And then what do you have? 7 times? 7 times 6 minus 1 times 4. And that's the? And then you get what?
3 times 6.
7 times 5 minus 3 times 4, and that's what? And then what do I put? Oh, minus right there, right? So what does this vector become? By the way, I write it like this so I can actually put everything out without writing it really long. You're welcome to do that. Just be really careful when you do it, okay? So what do you get? 18 minus 5 is? 13i minus 38j plus 23k. Do you agree with that? So what's cool is that's the cross product. That vector right there is perpendicular. If I wanted the area of the parallelogram, what would I do to that vector to get the area of the parallelogram? I would take the magnitude. So what would be the area of the parallelogram?
13.
The square root of 13 squared plus 38 squared plus 23 squared. This is super, super useful on many fronts. On many, many, many fronts. Okay, as practice here, how about I make up some vectors, okay? So let's say I asked you for, let's say I said J, I'm not using J, why am I using J? How about vector B is 1, negative 5, 3, and vector C is 2, 5, negative 4. Find me B cross C. Do that by yourself.